All right, class, welcome. Today, we're going to take a close look at what seems like a very simple circuit, a diode-switched RLC load. But don't let its simplicity fool you. Understanding what happens in the moments after we flip that switch, well, that transient behavior is the key to designing some of the most advanced and efficient power systems we use every single day.
Okay, let's get right to it. Our entire discussion today, it all boils down to answering this one central question. You see the circuit here? At time t equals 0, we close the switch. What happens to the current, I of t? I mean, what does it really do? Does it slowly ramp up? Does it spike violently? Or does it maybe ring like a bell? That's what we're here to find out.
So here's our game plan. We'll start by decoding this system's DNA, the math that describes it. Then we'll uncover the three possible realities of its behavior. From there, we'll get our hands dirty with a practical case study, check our work with a simulation, and finally, we'll talk about why any of this really matters.
All right, first things first. To understand any physical system, you have to learn its language. And for circuits, that language is mathematics. Our first job is to translate this collection of components into one precise equation that tells us everything we need to know.
So how do we build that equation? Well, we start with our old friend Kirchhoff's voltage law. We just sum the voltages around the loop, but you'll notice that gives us this pesky integral term, which is a bit of a pain to solve directly. So what do? We just take the derivative of the entire equation, and boom, we're left with the beautiful standard form you see at the bottom. That is the circuit's governing equation, its mathematical signature. And notice it's a second-order equation. Why? Because we have two independent energy storage elements, the inductor and the capacitor.
Now here's where it gets really interesting. Everything, and I mean everything, this circuit does from here on out is decided by a tug of war between two key parameters that are hiding inside that equation. On one side, we have alpha, the damping factor, and on the other, we have omega naught, the undamped resonant frequency. First up is the damping factor, alpha. You can think of this as the circuit's brakes. It's all about the resistor. Just like the shock absorbers in a car, the resistor's job is to dissipate energy, to burn it off as heat, and provide friction that fights against any oscillation and brings things to a halt.
On the other side of that tug of war is the resonant frequency, omega naught. This is the circuit's natural desire to resonate. It's the inductor and the capacitor playing a game of hot potato with energy, sloshing it back and forth. It's like a tuning fork. It just wants to ring at a very specific pitch.
So you have the brakes, and you have the engine's desire to ring. The crucial point here is that the outcome of this battle between alpha and omega naught, it dictates everything. And it turns out there are only three possible outcomes, three realities for a current element.
And here they are visually. First, what if damping is much stronger than resonance? If alpha is greater than omega naught, the brakes win. You get this slow, sluggish, almost lazy response. We call that overdamped. What if they're perfectly matched? That's the critically damped case. It's the fastest way to get where you're going without overshooting. It's the Goldilocks zone. And finally, what happens if resonance wins? If omega naught is bigger than alpha, you get exactly what you'd expect, oscillation. The system rings. We call that underdamped.
Now, each of these three realities has its own unique mathematical form, its own solution. But for us in power electronics, I want you to pay special attention to that underdamped case. You see that ringing, that decaying sine wave? It's not a bug, it's a feature. That controlled oscillation is a tool, a secret weapon we use to build incredibly efficient systems.
Okay, enough with the abstract theory. Let's get our hands dirty. Let's take a real circuit with some real component values and walk through how to solve for the current from start to finish. Whenever you face a problem like this, on an exam or in the lab, just follow this simple three-step recipe. First, characterize the system. Figure out which of the three realities you're in. Second, find the specific constants for your circuit. And third, put it all together and interpret what the result actually means.
Step 1. Characterize. We just take our R, L, and C values and plug them into the formulas for alpha and omega naught. It's just plug and chug. And out pop our two key numbers, an alpha of 40,000 radians per second and an omega naught of 100,000 radians per second.
So now we compare them. Damping is 40,000. Resonance is 100,000. It's not even close, is it? Resonance wins. And that tells us, definitively, that we are dealing with an underdamped system. We know, right now, before we do any more math,
this circuit is going to ring. Now that verdict, underdamped, is the key. It tells us which equation to grab from our toolbox, the one with the decaying sine wave. But that's general solution. We need to find the specific constants, A1 and A2, for our circuit. To do that, we use the initial conditions. We know that at the exact instant the switch closes, the inductor current must be 0, and we know the capacitor is charged to the source voltage VG. Those two facts let us solve for A1 and A2.
And voila! Here it is, the final expression for our current, and a plot of what it actually looks like. It's that beautiful decaying sine wave, just as we predicted. But look closely at what's happening. The current rises, peaks, and then as it tries to swing negative, bam! The diode slams the door shut. It says, nope, current can only flow one way. So we get just one single positive pulse. And the whole show is over in just 34.27 microseconds. Incredible.
The math is elegant. The graph looks great, but as engineers, we live by the motto, trust but verify. So let's head over to the computer, fire up a PSpice simulation, and see if reality agrees with our theory.
And we're not just going to test our one case. To really see the effect of damping, we'll run 3 simulations. We'll use our 160 ohm resistor, then a smaller one for less damping, and a larger one for more damping. This should give us a perfect picture of how the resistor controls the response. And would you look at that? The results are textbook, absolutely perfect. Our calculated case, the 60 ohm one, is right there in the middle, peaking exactly where our math said it would. You can clearly see that with less resistance, you get less damping and a much bigger current pulse. And when you crank up the resistance, the damping gets stronger, and it just squashes that pulse right down. Theory and reality are in perfect agreement. I love to see it.
Okay, so let's take a step back. We've done the math, we've run the simulation, we've seen it all work. So what? Why did we just spend all this time analyzing one tiny pulse of current?
Well, it really boils down to 3 core lessons. First, damping is destiny. The physical R, L, and C values you choose completely determine how the circuit will behave. Second, there are only 3 states. It will always be overdamped, critically damped, or underdamped. And third, and this is the most important takeaway for us, as power electronics engineers, we intentionally exploit the underdamped case to build better, more efficient technology. I really like this flowchart because it perfectly summarizes the journey we just took. And really, this is the engineering process. You start with a physical thing, you create a mathematical model for it, you analyze that model to get a solution, and then you verify that solution against reality. From a physical concept to a verified insight. That's the game.
So we come back to that final question. Why does this one tiny pulse, lasting only microseconds, matter so much? Because this isn't just an academic exercise. This principle, the art of creating and controlling a single, underdamped, resonant pulse, that is the absolute beating heart of modern, high-efficiency power electronics. It's the magic inside your laptop charger. It's how we're charging electric vehicles. By mastering this one fundamental circuit, you're not just learning to solve a problem, you're learning the language that will be used to design the future.